So I'm a volunteer at the National Museum of Computing, and I recently came across this poster. So there's this poster which is in a not great place in the museum. It's stuck to the right of a large computer that people don't tend to look up very much, and it's right by a fire exit. So it's not exactly a great place for it, but still. And on the right is a book, one of several books that she wrote. Now, this talk is going to contain a number of topics. Firstly, I'm going to give you a brief introduction to Kateryna Yushchenko, who's the subject of the poster that I just showed you. And then I'm going to talk about a programming language that she invented called the address programming language. And then I'm going to talk about another programming language which was created effectively somewhat later, which is a 3-address pseudo programming language and an interpreting simulator, which I have written. So the poster reads, her dates are December 8th, 1919 through August 15th, 2001. In 1950, Kateryna Yushchenko earned a PhD from the Ukrainian Academy of Sciences, making her the first woman in the USSR to become a Doctor of Physical and Mathematical Sciences in Programming. She was a member of the team who developed a computer called MESM, the first fully operational electronic computer in continental Europe. I would comment that MESM is the Russian name for the machine. In Ukrainian, bearing in mind that Kateryna Yushchenko was a Ukrainian, in Ukrainian it is called the MEOM. So if you're looking up references to MESM, you might find some to MEOM, but it's the same computer. The most famous contribution is the development of the address programming language in 1955, one of the world's earliest high-level languages. This language became the standard language used on computers developed in the Soviet Union in the 1950s and 1960s. What's in her name? She seems to have 2 first names. When her name is written in Ukrainian, her name is Kateryna, and the first letter of her name is obviously K. If her name is written in Russian, her name is Yekaterina, and therefore the first letter is E. Her initial is E. And that means books that she was writing, which were being written in Russian at the time, will show her first initial as E, and you can, even if you can't read Cyrillic, you could probably see it. This first character here is definitely the letter E. But today she is known as Kateryna. She wrote a number of books, the first one being Adresnoye Programovania, the address programming language. And then she moved on to write a book or co-author a book called Elementy Programovania. And this was co-authored with Gnedenko and Korolyuk, and her name appears last on the list. And this doesn't necessarily mean she was the least contribution, but it just happens that in the Russian alphabet, the first letter of her last name is second from the end of the alphabet. So the 2 gentlemen whose names preceded her, whose names start with the letter G and the letter K, preceded her. This was then translated. This book was translated into French as Éléments de programmation sur ordinateur, into Hungarian, and I'm not going to attempt to pronounce this name, and in German as Elemente der Programmierung. Now, going back to the address language initially, the address programming language, this is from a modern Wikipedia. And a translation of this is that the main innovative principle proposed by Yushchenko and her colleagues is the principle of targeting. And that's not a great translation, courtesy Google, because the Ukrainian up here clearly says adresnosti, which just means the principle of using addresses. Regarding the data used by the program, the principle is formulated as follows. The program does not specify actual numbers, that is to say, in the instructions, but instead it specifies addresses of memory cells which have been initialized with the necessary numbers. And this, of course, is something those of us who write software these days, who we think about this with no surprise, really. We're quite used to having data and programs separate and addressing items from the data area. Now, for example, and there's a number of examples on this Wikipedia site, stroke B pointing to A is the equivalent of the Pascal A : B, or the C language A = B. Two strokes before the first code indicates a dereferencing, a single dereferencing. So double stroke A pointing to B says that in C, for example, a language with which I'm more familiar than Pascal, B equals one level of dereferencing from A. And you can go up to 3 strokes and get double dereferencing in C. And the same applies to functions. And there's also the possibility of having a negative level of dereferencing. And let B be some number, then the operation -1 for the B equals A, which they call the // operation in translation, returns the address of the memory cell that contains the value B. Due to the fact that there can be many such values in memory, the given operation, where A is only one address, in general does not make much sense. It would be more correct to define an operation that returns a set of all memory cells that contain the value B. And they provide a little bit of code to explain the above paragraph. And if you would like to know more, then I suggest you Google address programming language on Wikipedia. There are about 8, I think, results to this. And the ones that are in Russian or in German or in French or in English are very, very short summaries. But if you select Ukrainska from the list of available languages, you get quite a full description of these operations. And of course, if you don't happen to speak Ukrainian, then Google Translate can be your friend. The book that I showed at the beginning is also downloadable. It's fairly heavy going, unless of course you happen to speak Russian. Turning now to the following 4 books, or 3 books, one book of which there are 3 translations: Elementi programmovania, Éléments de programmation sur ordinateur, the Hungarian variant, and Elemente der Programmierung. So, to emphasize, the original version is the Russian language version, which was published in 1961. And note that the authors were Ukrainian, even though the book is written in Russian. The German and Hungarian translations were published in 1964. The French translation was published in 1969. And these books do mention some computers in some detail. There's the BESM, which basically means large or high-speed computing machine, the Strela, arrow, the Ural, the M3, and the Kiev. This list is not the same in all the translations, and the Hungarian version, for some strange reason, includes the Elliott 803, a machine which, of course, we have at the National Museum of Computing. And the basic premises are that data is held in a series of floating point storage areas. There's a 3-address language to describe the instructions, and there's a pseudo code in these books which describes how to write software in it. This is a picture of the first computer I mentioned, the Bessum. I took this in the Science Museum in London. And here's an example, the very first program, which shows, first of all, the data area, Nomer Yachki, which is basically the names of the data items. The contents of those data areas, and the rightmost one is the result of the formula you're going to run. So you can quite clearly see A, B, C, D, and X, which match the data in the formula at the top of the screen, and Y, which is the result. Now, this program is written in this 3-address code, this is an example of that. So you have a Nomer command, and that's just n+1 down to n+7. Cod operacji, the operation code, and going from top to bottom, you have multiplication, addition, multiplication, addition. The colon represents division. The capital Pi represents printing, and the last line, it's don't be fooled, is OST in transliteration. There is a difference between a capital. There's a difference between an M, which has like sharp corners, like top in the caption in the top left column at the top, and the rounded M, which is in fact a T. And then to the right of the cod operacji, you can see 1A, 2A, and 3A, which are the 3 addresses which all of these instructions, with the exception of the last 2, use. And then you have in the rightmost column, rezultat operacji. And so you're multiplying A1 by A5, and that means you are effectively multiplying A by X. So the result of the operation, you now have AX in omega 1. You're then stepping through the formula until you end up with AX plus B divided by CX plus D goes into Y, and then you're printing the value Y, and then the program stops. I thought this was an interesting program, but not one that I would spend too much time on. So instead, I decided to steal program number 10 from the book, which was a square root algorithm. This algorithm uses the Newton-Raphson approximation method to calculate the square root of a given number. Column on the left is the values. So you have gamma 0, x, a half, and e, which are values which are used during the calculation. And on the right, we have the actual code. There is a new instruction down here at k plus 6, which is a conditional jump. And it compares the absolute values of alpha 4 and omega 2. And if it's greater than a certain value, the value in alpha 4, which is represented by this eta, then the program loops back to k plus 1. Eventually, the approximation, the difference between 2 sequential approximations becomes less than the value of eta, and the program stops. Now, I've rendered this into a notepad form. but it's effectively the same program. And I'm then able to execute it in my simulator. Oh, this is just a brief explanation of the square root by approximation, where a up here is the number for which the square root is sought, and x, n, where n starts at 0, is an initial guess, and you can choose any number you like that's less than the number you're looking for the square root of. For example, 1. It's a nice, easy start point. And this approximation series converges quite quickly. So that's my program, converted from the program 10 of the book. I've also introduced this instruction here, capital V, lowercase v, which is read cards or read a card, and I'm using the pi to print the output. I'll explain the layout of this in a little while. So I asked it to produce me the square root of 2, and it's run and generated the square root of 2 equals 1.412135 and so on. I'm using Microsoft double length floating point to do all my calculations, which is actually different from the machines that this software is emulating. But I'm not trying to produce an exact emulation, just something that's fairly close. On the second line, I then multiplied this square root by itself to get back a number that's pretty close to 2. And I then repeat for the square root of 3, and the square root of 3 is 1.73205, and so on. And the square of that goes back to almost 3. And that's reasonable accuracy, when you bear in mind that slide rules were good enough for putting men on the moon. Then this accuracy is quite good enough. I then moved on to example number 2, and you probably mostly recognize this formula, which is the finding the roots of a quadratic equation. Excuse me. Once again, we have the start values. A, B, and C are the values of the parameters in the quadratic equation. You have omega 1 and omega 2, in which the resultat appears, the result, and omega 3 and omega 4, robocie, which are working variable area. I'd mention incidentally that robocie is not unrelated to the word robot, which of course has come into standard English, albeit not from Russian. So we have multiplications, subtractions, additions, less than or equal jump, print, and the system actually provides a square root subroutine. So although I did square rooting in the previous example by hand, so as to speak, there's a square root function available. And the equation goes on, and you can read from the comments if you really want to what's going on, but in the end you end up with some results. And I set the start values to 6, 17, and 12, so I would have 6x squared plus 17x plus 12 equals 0, and set my system running. And it produces, interestingly, there's a line of all zeros, followed by the 2 actual roots, minus 1.3 recurring and minus 1.5. And I'm happy to be able to report that these match an online quadratic equation solver, which I found at the Maths is Fun website. The 0 is indicative that the roots are real roots. If the 0 line was missing, it means the roots are imaginary. So it says in the book. I would add, by the way, that when I started looking at the Russian version, I found myself a bit flummoxed in places, but then I was delighted to discover both the French and German versions, as my French and German are rather better than my Russian. Right, calculating e to the x, and that's a fairly simple sequence. E to the x is 1 plus x squared over 2 factorial and so on. And I've simplified this just calculating e by setting x to 1. So I have this fairly simple program down here, which when run generates the output value of 2.78, 718, 2818, and so on. The various stages of this emulator show how the emulator has developed over time. I've been working on this for maybe 3 months, and I've gone through multiple iterations of this emulator. Next, we have sine. Sine of x is x divided by minus x squared over 3 factorial minus x to the 4th over 5 factorial. I have to look on a different screen because I've got all the things that are telling me that I'm sharing my screen on top of part of my slides. This is my translation. This program uses radians, as you might expect, although personally I'm a degrees person, but I've kept it to radians. And the sine of 1.570796 radians is 0.999 recurring, 39229. I then decided to extend according to one of their exercises where they said, why don't you develop a program to do cos based on the sine? Cos h is square root of 1 minus sine squared h. So I added in some code to print the sine and then print the cos, and then also for a good measure to print the tangent. And also I'm taking the input angle in degrees because, as I said, I'm kind of a degrees person. So I'm starting off with 45 degrees, and it converts 45 degrees into 0.7853 radians. Now both the sine and the cosine of 45 degrees is 1 over root 2, and the tangent is 1. Moving on, pi. There's a fairly slow to converge sequence. Pi by 4 is 1 minus a third plus a fifth minus 7 plus 1 over 9. And we run this one on the Harwell Decatron which we also have at the National Museum of Computing. This program was written by a colleague of mine, Kevin, and it uses roughly 10, 11, 12, 15, 16 locations to create pi slowly. As I've mentioned, the Harwell Decatron here's a picture of it. It's switched off at the moment. But when it's switched on, you have this remarkable display. This is 5 words of the Harwell Decatron, which is a computer, also known as the Which memory. 5 words, and it's very shiny. So I converted this program into the 3-address language, and I leave it to run. And as you can see, it is run for a while, and it's still approximating 3.14179, 3.14139, 3.14, and it does take a lot of runs of this loop to end up with a value that's actually close to pi, and that's a known fact for this particular pi generation sequence. But it's fairly easy to program, which is why we use it. So thus far, I've implemented the following instructions: plus minus multiplication, 2 sorts of multiplication, division, the OST function, which in the French manual is referred to as ARR, which is just arrête, pi for print, capital V, lowercase v for read card or cards, equals and not equals, which are jumps along, conditional jumps along with the less than, e and equal, and less than and equal on absolutes, and the root instruction. In the third column, as I'm using a character set which is way out of the ASCII range, I'm using UTF-16 big endian. So plus is 002b, but I have two values of pi because one of them is the Russian pi letter, the Cyrillic pi letter, I should say, and one of them is the Greek pi letter. So I've implemented both of them. Now I've cheated a little bit with the pi instruction in that I've decided that it would be useful not only to have it printing, and I would add it's only printing to a file and to a list box on the display, but it would also be nice to have it displaying on a physical display. So here I have in the pi generation algorithm, I have a pi with lambda 1 as an operation, as an option, and lambda 2. And that's line 1 and line 2 of a 2-line retail display. And that means I can run the software and display interesting numbers as it runs on up here, rather larger than down here. So that means I've deviated even further from the original design. Another program which I then thought I would add is something called the Collatz conjecture. And I've been told that no mathematician who expects to be taken seriously should ever consider even discussing the Collatz conjecture. So, but then I don't really expect to be taken seriously as a mathematician. And for those of you who've avoided knowing about this subject, think of a number, a positive integer I. And when I say a positive integer, I mean greater than 0. I guess it should say that here. If it is even, divide it by 2, so that j equals I divided by 2. But if I is odd, then you multiply by 3 and add 1. So j becomes 3i plus 1. And then you loop back to line 1, having replaced I with j. Eventually, j will equal 1, at which point the sequence repeats indefinitely or infinitely with values 4, 2, 1. And the sequence is considered finished at the first instance where j is equal to 1. The as yet unproven conjecture is that the sequence will always end in the same way, regardless of the initial value of I. And I've never been able to prove that it doesn't, and neither has anybody else. Now, you have to work out at one point, you have to make a decision based on whether the number is even or odd. But fortunately, two further functions are defined, which are n in curly brackets and n in square brackets, which returns the whole number part of the number n or the fractional part of the number n in the reverse order. So I've added such instructions, and these functions extract the fractional part and the integer part. And that means I can do my division by 2. And if I get a value with a fractional part of 0.5 or 0.5, then I know that the number was odd. So I've added some code here to check for values to check for even, and then I can do jump if even, jump if odd. If it works out that it's neither even nor odd, then clearly something has gone wrong with something's drifted in the floating point, and it just falls through and stops. Some kind of rounding error has occurred. Otherwise, it just runs cheerfully to the end. So feeding the value 1, 2, 3, 4, 5, 6, 7, and running for a while, then eventually you can see on the printer, the virtual printer, 16, 8, 4, 2, 1, and then I'm printing the number of counts, the number of steps, 111. And of course, I've proven that on an online Collatz conjecture program. If I'm testing the number 1, 2, 3, 4, 5, 6, 7, then I'd expect the value of 111, which is exactly what I have here. So let's look at the way I've written the program. There are effectively 3 sections. The first section is the data area. So I'm using alpha1 space or name alpha1 equals a value with spaces before and after the equals. And then at the bottom, I've chosen to use 4 asterisks. And I'm only using 4 asterisks because a very, very long time ago, I used to program ICT 1900s, and 4 asterisks were used to indicate end of file in effect. But although I'm using this to mean end of section, you then have the program. And I've arranged my emulator so that I can actually write comments, which it will ignore. And these are an address, but in the original system, these are addresses, but in fact, I'm cheating and using these as labels. And then finally, there's a card section. So there's one card, which reads 1, 2, 3, 4, 5, 6, 7. I've added a second control file, which tells my emulator what program I want it to read. So now I can click on the Programs button. It gives me a list of available programs, and then I can click 1 or 2 or 3 for the top 3, and then the others I have to select by clicking on the names. There's a step, 1 instruction at a time option, a run where it just runs, a break if I want to stop running, and an exit button, exit from the emulator. Now on the screen itself, so let's start with these options. Well, let's start with option 2 first, which is the name. The first line of each file is going to have the name of the program or some commentary in the program. So it's collatz.txt and then hypothesa collatzia. And then the line above is the UTF-16 big endian equivalent. Item 3 are the addresses in the storage, in the data storage, and item 4 are the values. I have later gone on to merge these into one display box rather than having 2, because I was having difficulty keeping these 2 in step for longer, when there were longer numbers of data entries. 5 is the program and the instruction that's being executed. And this, of course, again, is all in UTF-16, is highlighted by the blue line. Excuse me. 6 is card input. 7 is tracing. And this program produces, at the moment, way more tracing than I could ever read. But it's better to have more tracing than less tracing. And then we have a printer. And this currently is just a list box. I haven't yet arranged for it to come out on a real printer. But what I do have is I am arranging for it to come out in a text file. So everything that was printed in the list box here comes out in this file. And these just 3 dots indicate where I've deleted some of it just for this display purposes. Excuse me 1 second. Now we come to 2 subjects, which are indexing and subroutine handling. You may have noticed thus far I didn't mention any subroutine calls. Well, I'm about to. But let's start with indexing. There's an instruction in the list of available codes, which is a plus in a circle. And this is saying plus in a circle, k plus 1, beta, k plus 1, where beta contains a 1. And you might think that this is an exclusive OR, but it's not an exclusive OR. It's an addition which adds to the instruction. So there's quite a clear differentiation between adding to an instruction and adding to a data location. And I have written this program here, which basically tests whether or not addition to an instruction can be made to work. And this produces, I'm adding to this multiply instruction, I'm adding the value S1, which is the value 1, to this instruction, so that the output, first of all, goes, in the first case, goes to omega 1, and the output goes to the next data location, which is omega 2, the next data location, which is omega 3, and so on. So as a, as a method of indexing within an array, if you will. So this is basically producing a table of squares. So it starts off by squaring alpha 1. But because I'm adding 1 to alpha 1, I'm also increasing by 1 the number which I'm squaring. And because I'm increasing the address in the instruction, the square is being put into various values. And you end up with a sequence of squares, 1, 4, 9, 16, 25, 36, and so on. And these can be printed on the printer, on the virtual printer. As well as plus in a circle, there is always minus in a circle for the reverse operation, although I haven't actually implemented that function. So I've now added quite a few more instructions because I've got O in a circle, plus in a circle, which I've also implemented as O and a separate plus sign. And there's O in the minus and minus, but I haven't actually got this one running as yet. There are then 3 more interesting instructions: BP, BPP, and BPRV. Subroutine call and return. Subroutine call and return from subroutine. And these, the first one is used in one circumstance, and the second 2 are used in a different circumstance. So BP is an unconditional jump, and it just jumps to a location. BPP and BPRV are unconditional jumps saving a return address in a return address register. So let's look at BP first and see what you can do with that. So here we have in storage locations gamma 1 and gamma 2, BP, P plus 4, and BP, P plus R plus 7. And these values are a little obscure, but when we come to this little flow chart, I hope it becomes more obvious. So in the beginning, you have some piece of main program, and it doesn't matter what it does, but it somehow generates a value beta, and you put the value beta into a storage location alpha. And the storage location alpha is used as a parameter to the subroutine Q. You then add gamma 1, which you may recall is a branch instruction, into n plus m plus 1. N plus m plus 1 is the last instruction of this subroutine. And then you do an unconditional jump to n plus 1, where n plus 1 is, for reasons that I won't go into at present, the first instruction of the subroutine. So it calls, and then eventually when it's finished doing whatever it's doing, it then exits. And because we set jump to P plus 4 in the return area, then we end up going to P plus 4, where there's a bit more main program which runs from P plus 4 to P plus R plus 3. Oops, excuse me. And then we add, this program produces some value gamma, which is moved into alpha, which is, as I mentioned earlier, the input parameter for the subroutine Q. Gamma 2, which is the jump to P plus R plus 7, gets moved into the last instruction of the subroutine. And then this calls the subroutine at n+1, and then when this exits, it exits back to p plus r plus 7, which is then you're now back in the main program. I hope you got all that. There might be a test, or there might not. Here's a test program which I wrote, and as you might imagine, it works. But then, of course, I wrote the emulator to make darn sure it would work. Now, that methodology works just fine, and other systems use something similar, putting a return address or return branch somewhere at the end of the subroutine. The EDSAC does it as a variant of that, for example. But this isn't always going to work, because some subroutines are provided as plug-in modules. So they're hardwired, plugged-in modules. And you obviously can't have the program fiddling around with the wiring of the last instruction of the subroutine. So a second approach arises, whereby you have the main program A, and then it calls the subroutine using a BPP instruction, which has the dual function of jumping to the first instruction of the subroutine and also putting the next address, p+2, into a physical hardware register, which is somewhere not on the screen, in fact. And then the subroutine runs, and then the subroutine has as its last instruction a BPRV, which uses the value that's been dumped in this physical hardware register to return to the next instruction. And then the process repeats for the second call of Q. BPRV then jumps to the new value, or via the new value of the subroutine return value. And then it moves on to C, and so on. And this works as well. So I had to add a return register. Note that this return register, there's only one of them. There is no stack. I don't think stacks had been invented at this point. So the return register is one depth only. So if you want to call one hardwired subroutine from another hardwired subroutine, then I'm afraid it's not actually possible to do that. So that's dealt with subroutine handling. And I thought I might just finish this off with a brief demo. I see not too many people have dropped out. Where are we? Oh, yes. So this is the Pi generation program. And I've already loaded the software. And if I can just start by doing some steps. So I'll just step the program step by step, and you'll notice immense amounts of tracing coming up here. And the first instruction of the first useful instruction of the Pi algorithm was to divide 4 by 1. And of course, 4 divided by 1 is 4 point several zeros. Interestingly, going off topic again, when we run the which version of the program on the which, 4 divided by 1 is actually 3.99999. But I suppose it's close enough. It's close enough to design nuclear reactors. And then the next value is somewhat less than 4, and that's 2.6. And so it runs and runs and runs like so. I hope you can actually see the numbers changing there. And I'm not going to leave it to run for very long because it takes quite a number of steps to finally converge on Pi. More steps than you probably have the patience to wait for. Yes, thank you kindly. So that's the demo. And are there any questions? Chiye Zapitanya. And you may unmute and ask.
I had a quick question, if I may.
You may.
I was wondering about the speed of the emulator. I didn't catch how fast these machines or the intended machine would run for this software. And I wondered whether you taken actions in the emulator to actually recreate the original performance.
No. And it's different on every different machine that I run it on. So this laptop is like 5 times faster than another laptop that I use, and that's just the way it goes. So I haven't actually tried to emulate the actual speed. And bearing in mind, this is the code I'm using is not real code. It's just a pseudo code that's used to describe programming on multiple different machines. So I mentioned there was the Besem, the Kiev, the Ural, the M3, the Strela, and I imagine they're all running at different speeds anyway. Anything else?
I have a question, Jerry. Thanks for the presentation. Very interesting. I just wanted to ask, is you know how in some financial institutions, even 40, 50 years later, you'll see that some really old code, COBOL, for example, is still used as part of the banking system. And I was just wondering, is that the case here? Are some ex-Soviet, I don't know, enterprises running this code?
Well, as I say, this is not a real code. It's a code for describing how to write software in basically an assembly language. So I don't believe they ever actually use this code. It's just an academic code, if you like.
Okay, because I noticed you mentioned 4 hardware types in an earlier slide. M3 was one of them. I'm just wondering, none of that is still in use then, or was ever in use?
I don't believe any of them are now in use, no. We have a Besem in the Science Museum, which hasn't been turned on for decades, as far as I know.
Okay. Oh, well, very old. Thank you.
There is a museum in Kyiv, which I'm hoping to visit when circumstances allow. But I don't know if they have anything that goes back that far.
Thanks for the tip. I'd like to see that too. Thanks.
Again, Jerry.
I'm sorry, did someone start with a question there?
Yes, I did. Ryan.
Hello.
Yeah, again, Jerry, there's not a place to visit at the moment, but in Moscow there's a big exhibition centre with different pavilions for different things. When I was there back in 1980, in the early days of Chairman Gorbachev and Glasnost,
yes,
I visited Moscow, and we were taken there as part of the in-tourist tour. But I had a job to get into the computer exhibition because, no, you don't want to see computers. You want to go to see the space pavilion. No, I don't. I want to see the computer pavilion. And I'm sure they had various of these machines there. I do know I've tried to go back by myself on the Moscow Underground on a sort of a free day. I can't remember how far I got. Whether I think I was redirected to the Space Pavilion again.
Oh, well. Well, interesting. Thank you. Well, I guess I will stop there.
Okay. Thank you. That was really
good. Day then, if not before. Okay. Cheers. Thanks.